Hello engineering students, Mr. O is here and we're going to go into the next level of method of joints. Analysis of trusses and finding out their internal forces across the members. I've got a question here. This is called question 11, example 11, you can call it whatever you want, but it is a relatively simple truss, bunch of triangles basically, and what it is supporting two loads up at the top. The question asks us to find the reactions in the supports of A and E. I have drawn that incorrectly. That should say E. There we go. So we have a question that is saying find the supports, the reactions of the supports of A and E, and also to solve for the forces in each of the members of the entire truss, using method of joints. This might seem like a very big question to you, but it is not that hard and not that difficult. All we're going to do is isolate each joint by itself as we go through it to solve the forces in each of the members. But firstly, before we start, we notice that we have this truss with the triangle shapes, but there is no angle on any of the edges here. And if we look at the distances, 3, 3, 3, and 3, and that particular distance from there to there, the height from B up to the member CD, what we can see is that we probably, that angle will equal that angle, will equal that angle, will equal that angle, just by the shape of the of this particular truss. So the first thing I would do is identify what particular members do I need to solve their forces for. So I'm going to go, starting on the left, I'm going to go, I need to solve what AB is. Then probably AC. BC as well. I'd say CD. BD. BE. And in the end, DE. So those are, I've now listed all of the members' forces that I need to find. Okay, what I also want to do, and as the first thing I do in most of mine, is redraw this so that I can draw all over it and go a little bit crazy. So let me draw it like that. It's going to be a really quick and rough. If you're doing an exam or something similar that has something like this, literally draw it like that. So what you do is you then try and work out what it is. It helps you then get a good gist of what's happening in the question. There's a force, 4 kilonewtons, 8 kilonewtons. I've got a distance, 4.8. And three meters, 3 meters, 3 meters, 3 meters. There we go. Okay, so now I'm going to try first thing first. I need to understand what the angle is over there, and by the looks of it over there, which is going to be the equivalent there and there. Let me look carefully. I have that distance and I have that distance. I have, if I want to solve that angle there, I'll do this quickly like this. I hope you can see that. 3 meters, 4.8. I want to solve that. I have the opposite and I have the adjacent. So opposite over adjacent is tan theta. If I want to find out what theta is, theta will effectively be tan minus 1. What is the opposite? The opposite is 4.8 divided by 3. Very quickly, I can solve that and go shift 10 minus 1, 4.8 divided by 3. 57.99. Hey, I'm going to round that up to be 58 degrees. 58 degrees. Based on that distance and that length, I would straight away say that is also 58. I'd say that is 58. And that is 58 degrees. If I want, I can work out what those are, but I'm not too worried about that right now. Okay. First things first, the question asked me to find the reactions at the supports A and E. Just like I did in the previous, I think it was question 8. I look at the bottom. Effectively what we have is we have a beam that looks like this. And three. That bottom set of members really acts like a beam with the forces of 8 kilonewtons pressing down there and 4 kilonewtons. Now, just before I carry on, I've got 8 and 4. I'm just going to call it 8 and 4 now. They're all the units are the same, 8 kilonewtons, 8 kilonewtons. Therefore, any other force that I work out across this truss is going to be in kilonewtons. So if I really quickly do a set of, I take a moments around A, sum of my moments will equal 0, and I take moments around A. As you know, sum of my moments counterclockwise will equal sum of my moments clockwise. Quickly resolving that into a set of formulas, or let me have a look at that. 8 from A, what is going to make my beam pivot counterclockwise, clockwise or counterclockwise? I've got clockwise on this side and I've got counterclockwise on this side. The only force that's going to make it go counterclockwise, which is in that direction, is going to be the force at E. So my force, my external force at E times 3, 6, 9, and 12. And what's going to make my beam pivot clockwise is going to be force times distance, force times 3. So it's going to be 8 times 3. And my force downwards, 3, 6, 9. There we go. And really, it's going to be, I'm going to, without doing all the hundreds of steps that I would normally do, I'm going to go 8 times 3, close brackets, plus 4 times 9, divided by 12, 5. So the force at my support E upwards is 5 kilonewtons. I'm going to assume it's upwards because it is still positive as well. The next thing I can do to work out what the force is at A. And I can do that really simply. Force, sum of the forces vertical equals 0. Sum of the forces down equals sum of the forces up. Pretty much defining my calculation, my standard formula is already there. If I look carefully, all the forces down are going to be 8 and 4. So that's 8 plus 4 equals all forces up. It's going to be, I'm going to assume A is positive. Force at A plus 5. And really, that's going to be 8 plus 4 equals 12. Bring that over to this side. Minus 5 is 7. Our force at A is 7 kilonewtons. So pretty much solve the reactions at my supports there and there. That's the force at those supports. That's supporting the load of this truss. Now, this is where I start now, my method of joints. Now, I'm going to try and solve the force in each of these members and find the force at each of the joints individually, using the external forces as well as then from the external forces working out what the internal forces and their direction of each of the members. I'm going to start off quickly with joint A. And what I do is I isolate joint A. And I stop and think about joint A. Joint A, and I'm going to start with the sum of the forces vertical. Sum of forces vertical at joint A. What do I know? I know that going into joint A is 7 kilonewtons. My external force applied to that joint is 7 kilonewtons. I want to solve for the angled member there. It's an axial load, but if I'm doing vertical, I can only work out and work with forces that are fully vertical. So there has to be a vertical force there. Because I don't know what it is, I'm going to assume that the AC force, AC vertical, is unknown. Okay? It is in tension. I'm going to assume it's in tension, therefore it's moving away from the joint. And if I do forces vertical, like I've done there, my forces down equal my forces up. Both of my forces applied to this, I don't look at the horizontal, I only look at the forces there. Okay? So my forces downwards, I have none. No forces downwards. Forces upwards, I have 7. And this vertical force, force AC vertical, I'm going to draw it here quickly. If this is 58 degrees, is the opposite. AC sine force AC sine 58 degrees. I bring the 7 over to this side, it becomes -7 divided by sine. I'm just going to go 7 divided by sine 58. So my answer is -8.25 kilonewtons equals FAC. Did you see how I did that? I took the 7, I took it to the other side, it became -7. And -7, all I had was on this side, -7 on this side. On this side it was force AC, which is the hypotenuse, sine 58. I divided by 58 and it gave me that answer there. It is in compression, therefore it is negative. Therefore it is technically force AC is 8.25 compression. And what I do is I go up to here and I go AC. AC is 8.25 compression. I've now solved the vertical of joint A. I've solved the vertical, but inadvertently I've also then solved what the force in the member AC is. Now I'm going to go at joint A, I'm going to do the sum of the forces horizontal are equal to 0. What I do now is I look at all the forces that are horizontal. Technically, if I look at my triangle, I know what AC is. It is no longer going away. It's not in tension, it's compression. So at that joint, it's actually going in this direction, into the joint. It's actually being compressed. So internally, it is pushing outwards. If my externally, if that member is being compressed, the internal force pushes towards the node. Therefore, if I try to resolve my vertical, my vertical is going to be going down, and my resultant will be AC, is going into the node. My horizontal force is going into the node, which is in compression. So what do I know at that joint horizontally? That my force AC horizontal is going in to that joint at A, 8.25, so it's 8.25. Let me ignore what I've just said there. It's going to be going in force AC is my horizontal force, because it is, here's my angle being 58 degrees. This is my adjacent. My adjacent is going to be my hypotenuse cos 58. And so it's going to be 8.25 cos 58. So I know what I do know is my horizontal force going that way, but I don't know what force of AB is. And because I don't know what it is, I assume it is positive, and I assume it is in tension. So it's moving away from the node. So technically, what I do is I go, well, the sum of my forces away from the node equals the sum of my forces to the left equals the sum of forces to the right. If my entire force around that node is going to be balanced. The force is going to the left, you can see directionally going into the node because AC is in compression, and the resultant of my horizontal is into the node. What I've got is I've got 8.25. I don't put the sign because I've already allocated my direction with this formula here. I've already said to the left, so already going that way is 8.25 in force, cos 58 degrees, and the force of AB that I don't actually know what it is. So I've assumed it's to tension and away from the node. This is, I can only use forces that are going in horizontal. 8.25 cos 58, 4.37 kilonewtons force AB. It is positive, and because it's positive, positive is tension. So straight away there, I've solved A, this one and this one. 4.37 tension. Often these types of questions will ask you to draw a force diagram when you're finished. I'm going to draw that over here so that I don't start to have to create the whole thing again. So technically I resolved that AC is in compression, which means at this particular joint the forces are traveling towards the node, and on the other side it is also going towards the joint, and it is 8.25 compression based on the arrows. I've just solved out what AB is. It's in tension, so they're moving away from the joint, and that is 4.37 kilonewtons. What's the next one I'm going to go? Well, I've now solved those two. I've got a force that's going vertically there. I've got a force that's horizontal, and I've got a force that is sort of at an angle. So it's going to have to be resolved into both its vertical and its horizontal. But I can only work with horizontal forces. I'll know that that's a horizontal force. I can only work, if I go vertical, I work with vertical and vertical forces only. AC can be resolved into a vertical force. CB can be resolved into a vertical force. So I can solve for CB or BC because I have the external force, the internal force, and I can solve for its equivalent, and then I just work it out there. So let's work that out. Let's go to joint C. Joint C, I'm going to go sum of my forces vertical equals 0, and I know that my up equals my down. So straight away I have a good idea, but let's draw the joint to have an idea what I'm looking at. So what I have my external force. My external force of 8 kilonewtons acting downwards. That's a pure vertical force there. I've got to keep my wits about me because I'm working with vertical only. The other one at that joint is AC, but my equivalent AC it is not acting downwards, because if you look at AC is in compression, it's pushing upwards. So technically it's going to be pushing against my force. AC vertical is pushing against that joint. And BC, I don't know what it is. I don't know what the equivalent vertical is. So I'm going to assume it's going away. It's going to be in tension. So I can work, I've got that. I can work that out quickly because I have what AC is, but I don't know what BC is. So I can actually solve that now. So let's have a look at that. Forces going down. Forces going down is going to be 8 plus the force BC, but its vertical equivalent. Its vertical equivalent is going to be this angle, the opposite. So it's going to be sine of 58. It's going to be force BC vertical, sine 58. Downward force, downward force. I have no more downward forces. Now that equals whatever the upward force is. What is force AC? Force AC vertical is going to be sine 58 times that hypotenuse. It's the opposite. The opposite is 8.25 times sine 58. All I do now is I take my 8 to the other side. FBC vertical equals 8.25 sine 58 minus 8 divided by sine 58. Force BC vertical, let's work this out. 8.25 sine 58 minus 8 equals divided by sine 58. Negative 1.18 kilonewtons. I know that it's negative, therefore it's in compression. So FBC is 1.18 kilonewtons. Technically should be writing kilonewtons there. It's in compression. So again, going towards the node and towards the node, and that is 1.18 kilonewtons. Now that I've solved the vertical, that's pretty much easy. I can do the same when it comes to horizontal. I'm actually squishing it right into the corner here by the looks of it. The sum of the forces horizontal. And let me find my little formula thing there. Whatever's going left, whatever force is applying left should also equal the sum, equal whatever force, sum of the forces going to the right. That's being in complete equilibrium. Let me draw that node as well. So what do we know about C load? At the particular node, what do I have? I have the horizontal equivalent of AC. It's going towards the node, so force AC horizontal. I can solve that easy because I know what AC is. I don't know what CD is, so I'm going to make it go again, away from the load. Force CD is a question mark. I do have an angled load there, which is BC, and I know what it is. It's going into the load, but its equivalent will be traveling in that direction then. So going into the node would be force BC horizontal. And there's my directions. Force AC horizontal is going that direction. Force CD, because I don't know what it is, so therefore it's in tension, it's going away from the node, so it's also going that direction. And then force BC going into the node that way, but technically its horizontal will be traveling forward. Its vertical will be traveling up and into the node that way, so that the resultant there is going in that direction. So let me just solve that then. So all my forces to the left is force BC cos 58 equals all the forces to the right, which is going to be force AC cos 58 plus force CD, which I don't know what that is. And we know that BC is 1.18, and we know that AC is 8.25. Technically, what happens now is (1.18) cos 58. That's on this side of the equation. I don't want this. I want this to go the other side. Let's go to the other side. So it's let me close the brackets. Subtracts 8.25 cos 58. FCD equals negative 3.75 kilonewtons. It's negative, therefore it's compression. .75 compression. Compression again. Forces going into the node, forces going into the node. 3.75. I rounded up to 7.5. Oh, we've solved 4 of them already. 1, 2, 3, and 4. This is quite a long question. We can probably do it on 1.5 times or 1.75 times speed to get across it all. Now, the next one I can do is BD. So I can go to joint B. Let me go to joint B. After a while, when you do these quickly, it will become like second nature. You'll be able to look at this very quickly, look at each joint, say, what's my resolve force of the angled member there? What's the vertical equivalent? What's the horizontal equivalent? And we'll go straight into it. It becomes a lot easier. So the first thing I'm going to do is I'm going to look at joint B now. And I'm going to go sum of the forces, vertical equals 0. And really, up equals down. But let's have a look at the joint. What do I have at this joint? At B, I'm going to ignore the the horizontal ones, because I can only look at vertical ones, and it's only that, and then it's only going to be BC and BD. And I actually need to solve what BD is, and I know what that is, so I can solve that really easy. So vertically, if I ignore everything else around here, including the bottom trusses because they're in perfect horizontal. What I'm going to do is I'm going to look at force BC vertical. I know it's going into the node because it's in compression, and I can solve that because I know what BC is. I don't know what BD is, so it's going to be going up. I'm going to assume, because I don't know what it is, I'm going to assume it's tension, so it's going to be positive going away from the node, and technically it's going to be away from the node, so up equals down, and this is going to be force BD vertical, and this way I can actually solve for that. Vertical is going to be sine, they're all going to be 58 degrees, so that's going to be pretty easy to solve. So technically what I can do is I can go the sum of the forces downwards, which is, what is BC? BC 1.18 sine 58, that's my vertical force, it's going down, equals, what's my force upwards? Because I'm going away from the node, I'm going to assume it's going away. I'm going to assume it's in tension. I don't know what it is, it'll solve itself. Force BD, also sine 58. This is quite a long video, I'm realizing. So really what happens is I'll solve that and divide it by sine. I divide that through by sine. They cancel each other out. And 1.18 kilonewtons equals FBD. It's positive, therefore it's in tension. That wasn't very hard. 1.18. And it's in tension. Tension is going away, it's going away. BD is 1.18. That's the force in BD. Let's have a look at the sum of my forces horizontal, because now I can solve for BE if I want to as well. This might get a bit tricky because now I have a horizontal force there. I have the equivalent horizontal force in BC. I have a resolved force of BD now as well, because there's an angle load onto it, it's going to be a force in, and then that's, there's going to be 4 different forces. Let me solve this quickly. I'll do this here and maybe do the calculations down there. So here's the node, here's B. So what do I have? BC is in compression, therefore the force is going into the node, and my horizontal is really going to be going into the node then as well. So force BC horizontal. I also have force AB, but it's going away from the node. I have force BE, which I'm trying to solve, going away. I don't know what it is, so I'm going to assume it's positive, which is then moving away from the node. That's force BE, so I can solve that easily. I've got AB, I've got to solve that. That I don't know what that is. And I've just solved for BD. It's going away from the node, so it's also traveling in that direction. And that is force BD, horizontal. It is AB is horizontal and BD. So there's 1, 2, 3 forces going in that direction equals a force going in that direction, or the other way around. So I'll just go and solve it here. Force AB, it's automatically horizontal, plus, well, it's going in that direction, equals force BC, horizontal, so it's cos 58 degrees, going in that way, plus FBE, I don't know what that is, but it is traveling in that direction, away from the node, because I've assumed it's in tension. I have no idea what it is, so I assume it's going away. And FBD, and that's going to be cos 58 degrees. And there we go. Let me just put the numbers in now, so it'll be easier for you to understand. 4.37 equals FBC 1.18 cos 58 plus FBE plus BD 1.18 cos 58. That's two of them. Interestingly, in order to solve that, I'll take both of those to this side and they'll become negative. So really, and you'll see in my calculator here, 4.37. That will go to this side, so I'm going to say subtract, open brackets, 1.18 cos 58, close brackets, minus again, oh, let me do two of those, because, well, I can just do that, minus 1.18 cos 58, close brackets, positive, oh wow. Did I solve that correctly, or did I make a mistake there? Let me double check that. 4.37. Okay. 4.37. Subtract 1.18 cos 58, and that goes over as well. Subtract 1.18 because BD is the same. Yep. Cos 58 equals FBE. 4.37 minus 1.18 cos 58, close brackets, minus 1.18 cos 58. I thought something seemed a bit odd there. It wouldn't be exactly the same. FBE is 3.12 kilonewtons and it's positive, so therefore it's in tension. BE is in tension, so it's moving away and away, and it is 3.12 kilonewtons in tension. And then I'm really just down to my last one, which is I can go up to there and solve it, but there's so many different forces. That one, I can double check it if I want to, or I can just go straight to this one. I know that's 5 kilonewtons. I know what that is, and that is 3.12 kilonewtons. So I'll just go to joint E because it's going to be simpler. Joint E, sum of my forces vertical. I'll do the vertical because it's easier. This is going to be 5 kilonewtons. My external force is 5. And my equivalent is actually going to be, I don't know what that is. But I know my horizontal, it's going to be the equivalent. So this, I don't know what the vertical is going to be. So my FDE vertical is all I can really solve. And because this is going to be the height is what I want, my angle is 58, I actually want the vertical. So they're both going in the same direction. Forces up equals forces down. So forces down is 0, forces up is going to be 5 plus FDE sine 58. It's going to become negative 5 divided by sine 58 equals FDE. 5 divided by sine 58. I know it's negative 5.9 kilonewtons negative. Don't forget that. And it's negative, therefore negative equals compression. I'll write that here. 5.9, sorry, I'll move my whole table. 5.9 kilonewtons in compression. And to finalize that compression towards the joint 5.9. And there is my answer. And I actually have a printout. I checked on the Valdivia truss simulator as well as the JHU truss simulator as well, and I verified that all of these are exactly the same, or exactly as the answers are there. Very long way to do this question. I apologize for it taking so long, but it really gives you the practice on looking at each of the nodes vertically, horizontally, vertically, horizontally, vertically, horizontally, and vertically, and I've solved the force and direction of every internal force on each member. And that's the method of joints for you. I hope that helps.